Hey everybody, Mr. Plant here, and today we are going to be doing an introduction to waves. We've been talking a lot about particles and how the model of the atom is created, and a little bit about light and light spectrum. And so now we need to get a little bit of knowledge on waves to give us some background knowledge so we can connect all those things together. So first and foremost is what is a wave? And really a wave is just a disturbance in matter that carries energy from one place to another. Right? So like sound wave carries sound energy from your speaker in your car to your ear and so on. Okay? The material that a wave travels through is what we call a medium. Right? You might have used medium for a different use and just normal life, but when we talk about waves, a medium is that material that a wave travels through. We really have two types of waves. We have transverse waves, which are kind of these classic up and down waves, if you can see my mouse, right? Up and down waves. And then we have longitudinal waves, which are these kind of compressed and expanded waves. So a transverse wave kind of looks a little bit like this. Now in your notes, make sure to draw this picture. There's going to be lots of pictures throughout this video. Draw these pictures. It's really important you draw the pictures and label them so you know what's going on with waves. So a transverse wave is just one where we start and we go up and down and up and down, perpendicular to the direction of the wave. So this wave would be moving to the right, and so a transverse wave then would go up and down. If the wave was moving down, then our wave would go kind of left and right. And we have some labels here like the crest, right? The crest is the top part of the wave. We also have something called the trough, which is the bottom part of the wave. Wavelength and amplitude we'll talk about a little bit later on in this video. Now some big examples of transverse waves are things like light. Light is a transverse wave, and radio waves. Right, how we get our music on the radio in your car, radio waves. Our second type of wave is something called a longitudinal wave. You might be a little less familiar with this. So a longitudinal wave, I like to imagine a slinky, kind of pushing and pulling a slinky apart. Right? As you push and pull it, you're making compressed and expanded waves. So if we look here at this waveform, we can kind of see the slinky on this left side is a little bit further apart, and then it compresses, and we call this portion compression, or I like to remember it as the squish, and then it expands out as it's kind of flowing through this. And this is called a rarefaction, or I like to call it the stretch. So we have the squish, or this compression, and the stretch, the rarefaction. Here our wavelength looks a little different, which again we'll talk about more later. Now the big example of a longitudinal wave is sound. Sound is hands down our biggest example of longitudinal waves. Think about like the speaker on your car, how it kind of pushes out and comes back in. Well, that's pushing air out and pulling it, pushing and pulling it, making these longitudinal waves. Another example are P waves and earthquakes. If you go back to freshman year and can remember earth science, we talked about P waves and S waves and surface waves. Well, P waves are an example of longitudinal waves. So now that we have those kind of two waves down, it's really important that we talk about these four characteristics of waves: wavelength, amplitude, period, and frequency. These four things can be used to kind of describe any sort of wave, and we're going to use them most of the time to describe transverse waves. You can use them with longitudinal waves as well, but for our purpose, we'll mostly be focusing on transverse waves. So the first one of these is wavelength. So wavelength, or this little weird kind of H-looking thing called a lambda, that's the symbol we use for wavelength, is the distance between a point on one wave and the same point on the next cycle of that wave. Now that sounds kind of crazy, but it's not too bad. Okay, just remember these are measured in meters, nanometers, right? They're measures of distance. So if we look at this wave, one wavelength is the distance between this first point on the wave, this first crest, and if we go down to a trough and all the way back up to the same point, making one full cycle, right? One full cycle, that is a wavelength, the distance from crest to crest or trough to trough, or you could even do this equilibrium point down, up. We don't stop at this next one because we're moving up. We need to be moving down. So down, up, and down. Okay, there's this distance that would also be one wavelength. Amplitude is our next characteristic we'll talk about. And amplitude is pretty straightforward. It is the height of the wave. It is also a measure of distance, so it's measured in meters or nanometers or femtometers, whatever kind of meter you're dealing with. And it is just the distance from this kind of equilibrium line to the top of the wave, right? The height, how tall the wave is, right? And amplitude is actually how we get AM radio, amplitude manipulation radio. I think amplitude manipulation radio, that's right. We change the height of the waves to get different radio signals. Okay, so amplitude, height. Period, then, is kind of the time it takes for one cycle to go by. So period is the time it takes for a wave to pass through one cycle. And remember, a cycle is a complete motion from starting point back to starting point. So if we start right here and we time how long it takes us to go from this point down the wave, hit the trough, go back up to the crest, and then stop, that is the period. Now it looks a lot like a wavelength when we draw it out, but the big difference here is it's measured in seconds. It's a measurement of time. So if we go from here, down the wave and up, that is one period, a measurement of time. Okay, so remember, period's a measurement of time. If we go back, amplitude's a measure of distance or height, and wavelength is a measure of distance from peak to peak. Okay, the final one we have is something called frequency. Okay, frequency is a measure of the number of complete cycles in a given time. So if period is the measure of how much time for one cycle, so the seconds in one cycle, frequency is the cycles in 1 second. Okay, so they're kind of inverses of each other. So we measure these in cycles per second, and this is something called a hertz, an HZ, hertz. Okay, so if we look at this graph, let's first count how many cycles we have. So we start at this point, we have 1, ending right after this 2-meter mark, and then we go up, down to the trough, back up again, 2. So we have about 2 cycles. Okay, and this says it took 2 seconds to do those 2 cycles. So if it's cycles per second, it's 2 cycles divided by 2 seconds. So our frequency in this case would be 1 hertz. All right, not too bad. Let's do a practice problem with that real quick. Okay, so the problem could say if a wave goes through 10 cycles over a span of 5 seconds, what is its frequency? Well, we know frequency is equal to the number of cycles divided by the amount of time. So in this case, we say a wave goes through 10 cycles, so our number of cycles is 10 cycles over a span of 5 seconds, so our amount of time is 5 seconds. 10 divided by 5 is 2. We get 2 cycles per second, and we know cycles per second is a fancy way of saying a hertz. So really our frequency then is 2 hertz. All right, guys. That's pretty much it for waves. We're going to talk more about light spectrum and how these waves tie into light and the spectrums of light and how that ties into particles next week. So make sure you have all of this down and that you are ready to come to class with questions so that we can be moving forward. Awesome, guys. I will see you next week.